Imagine a machine that can understand language from both directions at same time. Not just reading a sentence left to right like traditional models, but also right to left simultaneously. This breakthrough changed the entire field of natural language processing. In 2018, researchers at Google introduced a revolutionary model called BERT, which dynamically improved tasks like question answering, sentiment analysis, text classification, named entity recognition, and search engine understanding. In fact, Google search itself started using BERT to better understand user queries. In this video, we are going to dive deep into what BERT is, why it was revolutionary, the full BERT architecture, masked language modeling, that is MLM, training method, and why directional context matters. And by end of this video, you will have a clear conceptual understanding of how BERT works internally. So let's begin. The problem before BERT. Before BERT, most NLM models processed text sequentially. Popular architectures includes RNN, LSTM, GRU. These models read text one word at a time from left to right. For example, the bank of the river was beautiful. Here the word bank referred to river bank, not financial institution. But earlier models struggled because they only looked at past context, not future context. Even advanced models like OpenAI GPT originally processed text left to right only. This limited their ability to fully understand word meaning within context. Researchers at Google solved this problem using a bidirectional transformer encoder. That model became BERT. What is BERT? BERT stands for bidirectional encoder representations for transformers. Let's break that down. Bidirectional. BERT read text in both directionals simultaneously. For example, take a sentence, the cat sat on the mat. To understand the word sat, BERT look at left context the cat and the right context that is on the mat. So the word representation becomes context aware. BERT uses only the encoder stack of the transformer architecture introduced in the paper. Attention is all you need. This has been explained in detail in one of my video. You can go and check it out. Unlike sequence to sequence models, BERT does not use the decoders, representations. BERT generates dense contextual embeddings for every token, meaning the same word can have different embeddings depending on the context. For an example, bank in river bank and bank loan will have different vector representation. Let's have a BERT architecture overview. Now let's look at the architecture. BERT is essentially stacked transformer encoders, and this is its typical configurations. And the high level architecture flow is, first we have an input sentence, then it is tokenized, then the input is embedded, then we have a transformer encoder layer, and then we have a contextual word representation, and lastly task specific output layer. Let's discuss about the BERT input representation. Before text enters the model, it converts into three types of embeddings: token embedding, segment embeddings, and positional embedding. So the token embedding, each word is converted into tokens using word piece tokenization. For example, playing becomes play and ing. This helps handle unknown words and vocabulary efficiently. Then we have a segment embeddings. BERT can process two sentences simultaneously. For example, sentence A and sentence B. Segment embeddings indicate which sentence a token belongs to. Then we have a positional embeddings. Transformers do not inherently understand word order, so BERT adds positional encodings to represent the position of each token in a sentence. So the final input representation is for every token We have input embedding, which is equal to token embedding, which has segment embedding and the positional embedding. So let's understand the transformer encoder layer. Once embeddings are prepared, they pass through multiple encoder layers, as BERT is an encoder-only model. Each encoder layer contains two main components, that is multi-head self-attention and second feed-forward neural network. Plus it has residual connections and layer normalization. And all this is been discussed in our previous video. Go check it out. So multi-head self-attention. Self-attention allows each word to focus on other words in the sentence. For an example, we have a sentence. The animal didn't cross the street because it was too tired. The word it must determine what it referred to. Using self-attention, the model assigns high attention weight to animal. This helps BERT understand the relationship between words. And multi-head attention. Instead of one attention mechanism, BERT uses multiple attention heads. Each head learns different relationships. For example, one head may learn syntax relationships, another may learn semantic meaning. This allows the model to capture complex linguistic patterns. Then we have a feed-forward layer. After attention, each token representation passes through a position-wise feed-forward neural network, which has this formula. And this introduce non-linearity and feature transformation. Then we have residual connection and layer normalization. So every sublayer includes residual connection, then layer normalization stabilizes training. This helps deep model like BERT train efficiently. Pre-training task in BERT. BERT is pre-trained using two main objectives: masked language modeling, that is MLM, next sentence prediction, that is NSP. In this video, we will focus on most important one, that is masked language modeling. So the masked language modeling, the traditional language models predict the next word. For example, the sky is dash. But this still focuses model to read text left to right. To enable bidirectional learning, BERT introduced masked language modeling. How MLM works. During training, random words in the sentence are masked. That means they are hidden. For example, we have an original sentence, that cat sat on the mat. So after masking, the masked sentence becomes the cat sat on the mask. The word mat is now masked in the masked sentence. The model must predict the missing word. So the correct output should be mat. In masking strategy, during training, 50% of the tokens are selected for masking. Among them, 80% replaced with mask, 10% replaced with random words, 10% kept unchanged. This prevents the model from overfitting to the mask token. So why MLM is powerful? Masked language modeling allows the model to use both left and right context. For an example, the man went to the dash to deposit money. Using the left context, went to the and the right context to deposit money. The model predict bank. This makes BERT extremely powerful for language understanding. So what is the output representation? After passing through all encoder layer, we obtain contextual embedding for every token. BERT uses a special token, CLS. This token represents the entire sentence. For tasks like classification, sentiment analysis, the CLS embedding is fed into the classification layer. Then we have a fine-tuning of the BERT model. So after pre-training, BERT can be fine-tuned on specific tasks with very small modifications. For example, sentiment analysis by adding classification layer, question answering for predicting answer span, and named entity recognition for classify tokens. This flexibility is why BERT became one of the most widely used NLP models. So why BERT was revolutionary? BERT changed NLP because it introduced bidirectional context understanding, deep transformer encoder architecture, masked language modeling, and transfer learning for NLP. This dynamically improved benchmarks like GLUE and QUAT, and it influenced many later models including Roberta, Albert, and DistilBERT. So let's discuss some of its use cases and application. First one, that is text classification. BERT can be fine-tuned for tasks like sentiment analysis, topic classification, and spam detection, understanding input text to assign class table. Second, we have a name entity recognition. that is NER. BERT excels at NER tasks, identifying and classifying entities such as people, organizations, locations, or dates within text. Third, we have extractive question answering. BERT tackles tasks like finding answers within context, extracting relevant text from source documents to provide coherent response. And fourth, we have semantic similarities. BERT can be fine-tuned to measure semantic similarities between sentence or paragraphs, helping identify duplicate context-related information. So today we explored what BERT is, its transformer encoder only architecture, how masked language modeling works, and why bidirectional context is powerful. Understanding BERT is crucial because many modern NLP systems are built on top of it or inspired by it. And if you are working in generative AI, NLP, or LLM engineering, mastering these fundamentals will give you a strong conceptual foundation. If you enjoyed this deep dive into BERT, make sure to subscribe for more AI architecture breakdowns and GenAI tutorials. And in the next video, we will explore how BERT is fine-tuned for real-world applications and building a project on BERT model, that is fine-tuning the BERT model. Till then, see you in the next one.